This is our first problem on the buffer WebAssign, and it's a real challenging one, but it's a very important one. If you understand this problem, it's going to make things much easier for the rest of the assignment. Well, let's look at the question. Which ionic compound, they're saying a salt, that's what an ionic compound would be, if any, could be used to make a buffer with these acids and bases. And here's a picture of capsules that you can use to make buffers. Buffers are critical in chemistry. Need some buffers? This is where you could end up buying some. This is Mettler Toledo's site, and they make some of the world's best pH meters. And they also sell these little packets and solutions with very specific pHs. They'll guarantee that this pH has a pH of 9.18. You can then put your pH meter in there and find out if your pH meter is reading correctly. If not, you adjust it. It's used for calibration because there are a lot of things that you have to know the pH for exactly. If you're making certain products, this is one of the major tests. If you want to have something with a pH of 4.01, you can pick up 30 20 ml packets of these little solutions for $80 and be certain that the pH will be accurate down within plus or minus 0.02 for these pHs. You can buy this one that where the solution is where you get a real bargain for 250 mLs for $28, and its pH is going to be 7.00, but that last zero has that uncertainty of that 0.2. Now, the key thing to buffers is knowing that you're going to be using the equilibrium acid-base equations for it. The most important one is the one that's the Henderson-Hasselbalch, where if you've got a buffer, it's going to have a certain pH, you will have to know the acid that you're using with it and the base that you're using with it. Now, these aren't just any old acids and bases. These are the weak acids, and the base has to be matching that weak acid. You can't use any weak base. You've got to use your weak acid and its conjugate base, the A minus that belongs to that weak acid. And when you know it's pKa and you know these concentrations, you've got this pH figured out. The greater the concentrations of these two substances, the greater your buffer capacity is. The more stable it will be when you add stuff to it. The less likely it's going to change because these concentrations won't be changed much if you add an acid or a base to it. Now, the other thing that you should know about buffers is that you can't make a buffer from a strong acid because the conjugate base of a strong acid just doesn't exist. It doesn't act as a base. These acids, 100% ionized, and their anions can't be used to make a buffer because they're with a strong acid. So here we've got this list of strong acids that you're supposed to know for the AP exam. And not only that, realize that the Cl, Br, I minus, the NO3, and the ClO4 are not going to be used for buffer making at all. So it's a 2-for-1. You memorize these strong acids, and you know that these anions are not going to be involved in anything in terms of acid-base reactions. So those common strong acids that you should know about the AP exam, well, that takes care of strong acids. Well, what are the strong bases that we don't have to worry about? Fortunately for us, the strong base that we'll have to deal with in AP is the hydroxide. There's some other strong bases, the NH2 minus and a few other exotics, but not going to have to deal with those. And that hydroxide ion will be matched with one of our soluble alkali metals, sodium and potassium. You don't have to worry about sodium or potassium, so you can just cross them off. Well, let's look at what we have here. We have HF. Well, that's not one of the strong acids or bases. So we realize that we will be able to make a buffer from HF. That's a weak acid. HCl, remember, that is like one of the most common strong acids, and you're not going to make a buffer with it. Forget that. No. Let's see if we can find any other strong things here. Oh, here's one. Sodium hydroxide. That's a strong base. forget that. There's another one we have to worry about. You're not going to have to worry about sodium hydroxide as being a buffer. Now here we've got something that's interesting. We've got our nitrate. Well, that belonged to a strong acid. And we've got our potassium that's here. That potassium belonged to a strong base. So this on two fronts, because the potassium belonged to the strong base, the nitrate belonged to the strong acid. Forget it. So we only have to deal with three substances here. We can forget about the others in terms of buffers. So knowing strong acids and strong bases and our spectator ions is going to make your life easier on this problem and all the other buffer problems. If you can identify the HA and the A minus, you're on your way to solving 2/3 of that Henderson-Hasselbalch equation. We've got our HF. If we're going to make a buffer with it, here's our acid, our HA. Well, what's the A minus? Well, what's the other half of the HF? Fluoride minus. If you have HF and you know its concentration, and you have fluoride minus and know its concentration, then we can end up going to our Henderson-Hasselbalch and say, we got this, we've got this. All we have to deal with is the pKa. We've got 2 of the 4 values that are in here. Knowing what these buffers are is half the battle. Now, they asked here, we need to have a salt. If you're making a buffer, you just can't put an anion in there. You have to have it with its cation. And of course, sodium's a perfect one because we know sodium's not involved in anything. It's just a spectator ion. It's soluble NaF. Now, you could use potassium if you liked. And when you make buffers, usually you either see their sodium compounds, potassium. You could use cesium and rubidium, but those are really expensive and they won't do anything special for you. Anion of your buffer matched with a sodium ionic compound that you can pack in these little pills. Okay, we've got this first one taken care of. Next, NH3. This is one of the ones you have to memorize. Ammonium is a weak base. It's a commonly used base. And so there are the amines. If you have a organic compound, it'll be NH2. And these are bases because nitrogen can pick up another hydrogen. It has a pair of unshared electrons that can pick up an H+. So this is our weak base. If we're going to be making a buffer with it, we'll need the conjugate acid. Well, the conjugate acid has to have another H+ attached to it. It's got to have an H+. So here we've got our base and its conjugate acid. You've got to know those conjugates. Of course, we can't just buy ammonium ions. You're going to have to make an ionic compound. Remember that chloride we had, which isn't involved in acid or base reactions, that's the perfect match for this. Ammonium chloride. You make up a solution of ammonium chloride. It's going to be slightly acidic. You mix it with some ammonia, and you've got yourself a buffer. So this is a nice contrast where we have a weak acid, and we get its anion, and we match it with a spectator cation. Here we've got a weak base. We give it an extra H+, and then stick an anion on it. Now, this is an interesting one. This is H3PO4, and it's used a lot in buffers. It's very versatile. It's inexpensive. It's stable. It's phosphoric acid, and we're going to try and make a buffer out of it. Well, we've got the acid. Therefore, we need its conjugate base. We get rid of one of the H+. With the base, we added an H+. With the weak acid, we remove an H+ to get the conjugate base. And again, we've got a minus charge here. And we're going to have to match something with it to make it a solid. And therefore, you can make a sodium phosphate with it, or you can make a potassium phosphate if you wanted. Okay, potassium, forget about. Nitrate, forget about. Strong base, strong acid conjugates. Sodium hydroxide, we're not worried about. Here's the toughest one of them all. This is sodium carbonate. Now, there's no hydrogens here, so this is going to have to be the weak base. It's a tricky one. First of all, the sodium's not going to do anything. We're not worried about the sodium, so all we have to do is worry about the carbonate. Our carbonate is going to be the base. So we just need its conjugate acid. So we've got a base here, a weak base. We're going to have to match it with its conjugate acid. Well, what do you do if you've got a weak base? You add an H plus to it. So we can do that. Here, we've added an H plus to our carbonate. And now it's an HCO3 with a -1 charge. We put an H and a plus here. Well, we can buy sodium carbonate. That's an ionic compound. It's a nice powder, cheap. It's washing soda. Well, we're going to need some HCO3 with it. What do? We add a sodium, an Na+, and we get baking soda, NaHCO3. You've got our salt here, our weak base, and here we've got its conjugate acid, the NaCO3. We're on our way to identifying an acid and its conjugate base. That's your first problem on this web assignment, and you're ready to go on to the next.